This video is going to continue with the topic, what decides how fast a river flows? In this video, we're going to be looking at biological applications of fluid flow.
In this video, we're going to look at some of the biological applications of fluid flow. So we'll be considering the flow of blood around the human body. So before we start, just a bit of a warning. With these physical theories, we always have to simplify the systems before we apply them. So we're going to make some assumptions which dramatically simplify the flow of blood around the human body. And this does mean that we do lose out on some of the details in the process. So in the School of Physics at UNSW, we do actually have a research group which researches biophysics. They have a particular interest in proteins and membranes and modelling these and using physics to describe what happens in these systems. They make a lot less simplifications than what we're going to make in this video. But to be able to use the physics, we do need to do this simplification. So to start with, let's start by describing some of the biology behind how the human heart works. So the human heart, like the heart of all mammals, has two circulatory systems. It's got two jobs. First of all, it takes the oxygen-poor blood, which is full of carbon dioxide, from the body, and it takes it to the lungs where it swaps the carbon dioxide for oxygen. It then takes the blood from the lungs back to the heart. It takes it back to the left side of the heart. And from the left side of the heart, this oxygen-rich blood is circulated to all the cells in your body. When it gets to its desired location, the blood swaps the oxygen for the waste product, carbon dioxide, which the blood then carries back through the veins to the heart. And so that is how the two circulatory systems work. We have blood flowing from the heart to the lungs, and then oxygen-rich blood flowing from the heart to all the cells in our body so that it can do its job supplying those cells with oxygen. So the heart itself is a really strong muscle that consists of four chambers. We've got the left side and the right side. The left side is the one which needs to supply the blood to everywhere in our body. So to do this, the ventricle on the left side contracts, decreasing its volume, and this increases the pressure, pushing the blood through the arteries to our body. So typically in a human, our heart, when we're resting, beats 72 times a minute, and each of those beats carries 70 millilitres of blood away from the heart to the body. So typically we have about 5 litres of blood each minute flowing through our veins, which coincidentally is about the volume of blood in the human body. So it takes about a minute for the blood to circulate throughout the human body. So in the human body, as in all biological systems, we've evolved so that form meets function. With the blood vessels, the arteries and the veins and capillaries that carry the blood around, they all have smooth cells on their surface. So these smooth cells reduce the turbulence and mean that the heart doesn't have to do extra work to provide extra energy to carry the blood around the body. The arteries, which carry the blood away from the heart, are very strong walled because the arteries carry the blood which is under a very high pressure. The veins, on the other hand, have much smaller walls because veins carry the blood back to the heart, and so it's not under as high a pressure. We saw in the demonstration of the Bernoulli effect that when we had the wide pipe, which was close to the tap, it had a higher pressure than the wide pipe further from the tap because you had to do work getting from one to the other, and so the total amount of energy and hence pressure dropped. So as your heart beats, right when it contracts, you have the highest pressure. So your heart contracts, pushing all the blood out of the left ventricle to go around your body, and then it relaxes. And when it relaxes, it fills with blood so that it's ready to pump again. And so this means that there's actually pressure waves traveling through your arteries and your veins. You've got the maximum pressure just when the heart has contracted and pushed all the blood out, and then it relaxes and the pressure drops off. So to compensate for this pressure change, arteries are actually elastic. So they can move a bit, and they do this to try and reduce those pressure changes. So if you feel on your wrist, you can actually feel this movement, which is how you feel your pulse moving through your body. So blood flows from the arteries, which are really fat tubes, the aorta is the main one coming out of your heart, into much narrower capillaries. So the capillaries have much thinner walls, and this is to allow the oxygen and carbon dioxide to be exchanged through those walls. So we saw that the volume flow of a fluid was constant. So the cross-sectional area times the velocity of the fluid through the pipe should be constant. So you may think, well, the velocity through those much wider tubes has to be a lot greater than through the narrow tubes. But this isn't actually true, because when the blood flows out of the arteries split up into a lot of capillaries. So the total surface area of the capillaries is actually much greater than the surface area or the cross-sectional area of that artery. So as the cross-sectional area is in fact increasing a lot, the velocity actually decreases. So the velocity of blood coming out of your heart through the aorta is about 48 meters per second, whereas the velocity of blood flowing through the fine capillaries is about 0.1 meters per second. You actually need that slow flow of blood through the capillaries to allow time for the oxygen and carbon dioxide to be exchanged. The other formula that we've seen for fluid flow, Bernoulli's equation, is also important. Your height actually has a large impact on the pressure of the blood in your veins. So my head is around about 30-35 centimeters above my heart, and in a minute we'll calculate what change of pressure that causes. But this is why humans have evolved to faint. If you get low pressure, you faint so that your heart and your head are horizontal with each other, they're at the same height, and this means that the pressure at your head will be equivalent to the pressure at your heart. So typical humans have a pressure when the heart contracts of 120 millimeters of mercury. So those are the old-fashioned units which were first used to measure pressures. If we want to get from millimeters of mercury into pascals, we need to multiply by 133. When the heart is relaxed, the typical blood pressure is 70 millimeters of mercury. So let's now calculate the pressure difference between my heart and my head.
So to do this calculation, we'll assume that my head is 35 centimeters above my heart. We're going to need to make use of the density of blood. So the density of blood can vary a bit, but we'll take it as equal to 1050 kilograms per meter cubed. We're going to make one other assumption. We're going to assume that the diameter of the blood vessels doesn't change between the heart and the head. So this assumption lets us use the rate of fluid flow equation, the volume rate of flow, AV is equal to constant, and this is the cross-sectional area, and if the diameter is not changing, then this isn't changing, so this is constant. So this tells us that the speed is the same at the heart and the head. So let's use Bernoulli's equation now. We've got that the pressure at the heart plus the density times g times the height of the heart plus a half rho times the velocity at the heart squared is equal to the same thing at the head. So the pressure at the head plus rho g times the height of the head plus a half rho v squared at the head. Now we've just said that the speed is the same at the heart and the head, so these are the same and the density is not changing, so this term and this term are identical, and so they will cancel each other out. So now what we need to do is work out how the pressure changes, and that's going to depend on this height here. So let's rearrange this. What we're trying to do is work out the pressure at the head. So we're trying to find this term. So we've got that the pressure at the head is equal to the pressure at the heart plus the density times gravity times the height at the heart minus the height at the head. So now what we can do is we can substitute in. Now let's do it for the maximum pressure. So that's when the heart contracts. When the heart contracts, the pressure we said was equal to 120 millimeters of mercury, which is equal to 120 millimeters of mercury times 133 to get it into pascals. Plus we've got the density of blood, which is 1050, times gravity, which is 9.8. Now the heart is 35 centimeters below the head. So the height of the heart minus the height of the head is minus 35 centimeters. So that's minus 0.35. So now what we can do is enter this into the calculator, and what we end up with is 12,358 pascals. So if we want to convert this into millimeters of mercury, we have to divide by 133, and if we do that, we end up with 93 millimeters of mercury. So the pressure at your head is lower than the pressure at your heart, as you'd expect, because there's some drop in pressure to do the work to pump it up there, and so the pressure up here is equal to 93 millimeters of mercury. And so when you faint, your head and your heart are at the same height because you're generally lying horizontal on the floor. And so rather than being at this decreased pressure of 93 millimeters of mercury, your head is now at the same pressure as your heart. And so that makes it easier for your heart to force the blood into your head, which is why we have evolved to faint. So we've considered the pressure difference between the heart and the head of the human. How about for a giraffe? So a giraffe's head is typically 2 meters above its heart. So a giraffe has a head pressure, like a human, of about 90 millimeters of mercury. And let's calculate what pressure does it need at its heart in order to have this pressure at its head. So we'll make the same assumptions as for the human, that the velocity of the blood flows the same because the blood vessels have the same diameter at the heart as at the head. So we've got the same equation, that the pressure, except that it's rearranged now, the pressure at the heart is equal to the pressure at the head plus rho g times the height at the head minus the height at the heart. And we'll assume that the blood of a giraffe is fairly similar to the blood of the human, so the density of the blood is 1050 kilograms per meter cubed. So let's substitute everything in. The pressure at the head is 90 times 133 pascals, so this is the 90 millimeters of mercury, and we're converting it to pascals, plus the density, which is 1050, times gravity, which is 9.8, times, now the head is 2 meters above the heart. So if this is H heart, this is H head, and this minus that is equal to 2 meters. So this is times 2 meters. And so we end up with 32,550 pascals, which let's just divide by 133 to convert it into millimeters of mercury. We've got 244 millimeters of mercury. So this has got a lot more blood pressure in its heart. So giraffes have very large hearts and very strong blood vessels to cope with this higher pressure. So the giraffe actually has some issues when it lowers its head to drink some water, because then its head is below its heart and its head is used to having pressure which is quite a lot lower than the heart's pressure. So the giraffes actually evolved with a couple of mechanisms to cope with this. When the giraffe lowers its head, it's inbuilt that its heart rate actually decreases to decrease its pressure. It also has one-way valves in its veins, so these let blood flow in this direction but not in this direction, and that stops all the blood pooling in its head when it lowers its head for a drink. So the other issue for the giraffe is that it has very high pressure in its legs here. So its legs actually have very firm, strong skin on them, and they're quite narrow to stop them swelling outwards under that much higher pressure.
Now another problem that comes about because of Bernoulli's equation and the relationship between pressure and height is how the blood gets back from our legs to our heart. To get back from our legs to our heart, the blood needs to do work to overcome that gravity which is pushing it down. So our bodies evolved several ways to help with this. First of all, some of the veins have small contractions in the wall to help push the blood along. Next, when we inhale, the volume of the veins near the heart actually increases, which fills them with blood, and so this has the effect of sucking the blood up. The biggest help though is when we exercise heavily, the muscles in our legs near the veins actually contract and expand into the veins, and this causes the blood to flow up to the heart. Now this actually has some risks associated with it. If you exercise heavily, then your body realizes that it needs more oxygen, and so your heart rate actually increases and you pump blood through your body much faster. So if you're exercising heavily, your heart rate's increased. If you then suddenly stop exercising, that third mechanism for returning blood from your legs to your heart goes away, the contraction of the muscles while you actually exercise. So this means that if you exercise heavily and then suddenly stop, you can end up with not getting enough blood to your heart. So if your heart's at all weak or there's any problems with it, this can be a big problem. So this is why everybody advises you to, after you've exercised heavily, have a bit of a cool down period where you exercise lightly to allow your heart rate to return to its normal resting rate before you completely stop exercising. There's several health problems that can affect the size of your arteries and veins. So affecting the size of the arteries and veins will affect the speed of the blood flow through them and also the pressure in them. So one of these problems is an aneurysm. An aneurysm is when a vein, or more particularly an artery, expands. So this can happen because you've got weakened arteries, and so it can be a hereditary thing, or it can happen as the result of some other health effect. But if the cross-sectional area of your artery increases, then the velocity of the blood flowing through the veins is going to decrease, and as a result of this decrease in velocity, you're actually going to feel an increase in pressure, which means that there's going to be more pressure, more force on the walls of that artery, and as a result of that, it's more likely to rupture. So let's have a look now at some of the details of what can happen in an aneurysm.
Okay, so the question is, an aneurysm can double the cross-sectional area of a blood vessel. If the velocity of the blood in the vessel is normally 0.40 meters per second, what does it become at the aneurysm? What is the change in pressure on the wall? So to work out what the velocity of the blood is, we're going to need to use that the volume flow rate is constant. So the cross-sectional area at place 1 times the velocity at place 1 is equal to the cross-sectional area at place 2 times the velocity at place 2. And let's call the place with the aneurysm place 2. So we've got A2 here and we've got A1 here. So the cross-sectional area 1 there and cross-sectional area 2 here. And we know that A2 is equal to 2A1. So what we're trying to work out is the velocity in this aneurysm. So we've got that the velocity in the aneurysm is equal to A1 V1 on A2. And now we'll substitute this in here. So we've got A1 on 2A1 times V1. And so this is equal to 0.40 on 2, which is equal to 0.20 meters per second. So we've now calculated the velocity of the blood through the aneurysm. Now what we're asked to do is calculate the change in pressure on the wall. So what we need to do is calculate the pressure in here. So to do the pressure, let's do it over here. We're going to need to use Bernoulli's equation. So we've got P1 plus a half rho V1 squared is equal to P2 plus a half rho V2 squared. We've left the rho GH terms off because these are at the same height. So this term is the same on each side of the equation. So they would cancel each other out and hence we've left them off. So what we want to know is what's the change in pressure. So we want to calculate P2 minus P1. So we subtract P1 from this side and then on this side we've got a half rho V1 squared minus V2 squared. So this is equal to a half. Now we'll need to know the density of blood. So we were told previously that the density of blood was equal to 1050 kilograms per meter cubed. So we'll use that same value. So this is 1050 times V1, the speed in here was 0.40 squared minus 0.20 squared, the velocity in the second part in the aneurysm that we calculated. So solving this on the calculator, we end up with 63 pascals. So that's the change in pressure between here and here. So it's at a higher pressure in here. And so because pressure is equal to force over area, if we've got a higher pressure, then we've got a higher force exerted on those walls. Force is equal to pressure times area. And this area is the surface area of the aneurysm, which is greater than the surface area of the normal wall. And so the force of the blood on the walls of the aneurysm is quite a lot larger than the force of the blood on the normal walls. And so this increases the risk of the rupture.
Another health problem is as we eat lots of fatty foods and high cholesterol foods or we smoke, we can get fatty deposits on the walls of our arteries and veins, which narrows them. So this is called arteriosclerosis. And as a result of this, it can cause the blood to flow much more quickly through those arteries or veins. So let's have a look now at some of the details of this.
So a blood vessel is reduced in size from 3 millimeters to 1 millimeter in diameter by fatty deposits on the walls. How does this affect the flow of blood? So we know that the volume rate of flow is constant. So AV is equal to a constant. And so what we need to do is work out the cross-sectional area. Now this is for a circular tube. And so the cross-sectional area is the surface area of a circle. So this is equal to pi r squared. And the radius is equal to half the diameter. So this tells us that the surface area is equal to pi times d over 2 all squared. So that's pi d squared on 4. So we know that we've got A1 V1 is equal to A2 V2. And when it's been reduced, we've got this diameter, D2 is equal to 1 millimeter, and D1 is equal to 3 millimeters. So we've got A1, which is pi on 4 D1 squared, times V1 is equal to A2, which is pi on 4 D2 squared V2, just substituting in for the cross-sectional area from down here. And so these pi on 4s will cancel each other out, and so we've got the velocity through the reduced section is equal to D1 squared times V1 over D2 squared. And so D1 squared, that's 3 millimeters squared, so that's 9 millimeters over D2, which is 1 millimeter squared, so that's 1 square millimeter, times V1, and so it's 9 times V1. So it has to flow 9 times as fast through this affected region. So it flows 9 times as fast through the narrow region.
So luckily we've developed medical techniques to deal with this arteriosclerosis, the narrowing of the arteries and veins. You can have what's called angioplasty, which is a small medical procedure where they put what's effectively a balloon into your artery or vein. So they put a little narrow tube and then they pump it up with a balloon, and this widens your artery or vein, and so that the blood flow can return to normal. So in this video we've seen that these equations for fluid flow have applications for the flow of blood around the human body, as well as applications for how fast a river flows. In the next video we're going to be looking at dams and how a dam in a river can change the flow of the river, but more importantly the dam can be used as a source of energy for us to use.
So I'd like to thank Sebastian Frick for filming this video, and also to these people for providing images with the Creative Commons license that we made use of.